The central theme for this unit will be looking at integrals and constructing integrals by thinking of objects as being sliced up and then using the integration technique to find the sum of the volume or the area of each of those slices. And you'll find the same general procedure as we go through all these examples. The first question is always going to be, how are you going to slice up the object? And typically that'll be either parallel to the x-axis, in which case you have delta y slices, or it might be vertical slices, each delta x thick. Those are typically the two we'll see. If you go on to study a vector calculus class, there are fun ways to do this with polar coordinates and radial coordinates, spherical coordinates. For this class, we'll stick with the two axis directions, x and y. Once you've decided how to slice, the next question is, how can you find the area or the volume of a representative slice? And here's the key thing that trips up many students. Don't try to overthink and find the area of one slice, but find the area of a slice in general and get a formula for that area. Those are the two hardest parts. Once you get to the area of a generic slice, well then we know that if we add up all those areas, we get the total area. And then, well, we can write that as an integral instead of a sum. The last step, evaluating integral, tends to be fairly straightforward in the examples we see here. The challenge is really in these first two stages, visualizing and deciding how you want to slice it, and then finding the area of a generic slice. So we saw one example previously. Let's take a look at another example now. So here we're asked to find the area between x equals y squared and y equals x. And we note here the two curves. Y equals x is the straight line, and x equals y squared, which is also possible to write as root x equals y, as the boundary of this square root function here. And the area we're looking for is the region enclosed between those two curves. Now here we've given you the direction to use horizontal slices. You could evaluate this area using vertical slices as well. There's no difficulty. We're going to do it with horizontal because that's less familiar for most students, and so it's good practice. So, first step, decide which direction you're going to slice in. That's already done. So let's imagine what those slices will look like. Pick some representative rectangles. And it's a little convoluted because we've got a boundary, a changing boundary on both the upper and lower ends. But as we make our rectangles thinner and thinner, we would see that the rectangles will approximate better and better the actual curved shape of the square root and the diagonal line of the y equals x curve. So let's go back to the basics then. Find the area of a generic slice, or of one rectangle in this particular case. So if you look at one rectangle, it's going to have two dimensions, a height and a width. And those two dimensions are going to be made up of delta y for the height. Each of these slices will have the same height, delta y. And then the width is going to be this distance here. Let's make that a little more clear. That's going to be our width. Now, how do we get that width when it could be the width at the peak, and it could also be a width down here, or a width when the rectangles are particularly large? How can we find that in general, or the volume, or sorry, the area of a generic slice? Well, what are the pieces that we know? What defines the boundary of that slice? Well, one of the boundaries is the graph y equals x, x equals y. And the other boundary, notice I'm focusing on the x because these are x distances. I'm drawing everything from left to right, so we're talking about distances between x equals 0 and x equals the boundary of our curve. The other boundary over here is x equals y squared. And so the width, we can think of it as the largest x minus the lowest x. Here's the whole length, and then I'm going to subtract away the shortened length, and I'm going to be left with the width of the rectangle I want. And so we can think of this as x upper, and this is x lower. I take the upper x and subtract the lower x. So our height delta y. The width is the difference between two different x coordinates, and we know that the upper x is defined by y itself because of the graph being y equals x, and on the lower side, the lower x is y squared. So literally, when we do this translation, we're using the functions that were given to us. Y equals x is being used explicitly here to get one of the boundary values. X equals y squared. We want the x distance here subtracted away from this other x distance. So we subtract off that x. Oh, but we want it in terms of y because we're doing delta y slices and we'll need an integral in terms of y. And so we say, well, we don't want x, we want what it's equal to, which is y squared. All right, this does take practice, so take a look at the practice problems as well as a reference. This is the hardest part. Once we have arrived at this stage, the area of one rectangle, to find the total area, it's simply a matter of writing this out as a sum and then an integral. In fact, at this point, I think we can jump to the exact total area as an integral. What we want to do is add up each of these slices, but we want to do so with delta y being smaller and smaller, or what we called dy. Then we also had our widths. They go in here, y minus y squared, and because it's the total, we're adding up all those areas. And the last little piece is to recognize what the limits of integration are. We have y here, and we're going to go from y equals something to something. Well, on the graph here, it's pretty clear that we're going from y equals 0 up to y equals 1. The integral from 0 to 1 of y minus y squared dy. Just as a quick ballpark, notice the square here is 1 unit, so we're expecting a value pretty small, certainly less than 1, maybe a fifth, a sixth, something like that. Certainly well below half even. So let's take a look and see what we get. At this point, we can ignore the area interpretation of this. The calculation comes back to the fundamental theorem and antiderivatives. Y squared over 2. So we antidifferentiate each of those, and we're going to evaluate the antiderivative at the limits 1 and 0. We get a half minus a third. Subtract the lower limits, that's 0 and 0, and in fact we actually get 1/6 square units. So this area here is exactly 1/6 square units. The key thing is that the integration, once we get there, is typically straightforward. The challenge is setting up the area integral in the first place. Let's go back one page. And that's to recognize how we got that integral in the first place. The area was, this entire area was broken up into small rectangles. We decided which way to slice it. And then we found the area of a generic slice. And then used that, just plugged it right into an integral to find the total area. And that same procedure is what we're going to use throughout this unit.